OK， 所以呢，延续着期中考前讲完的这个 Martian model，OK，sorry，forgot it's the English class. So continue from what we learned from the previous model. We will talk about the next growth model, which is the Solow growth model. And based on my understanding, a lot of you should have learned this before. Okay, so for the mathematical part, I actually will go it maybe a little bit faster than even the previous model, even though the previous model should be the easier one. But this one, you should have learned somewhere before, right? Okay, so this model, different from the previous one, we assume that there is a population growth. Okay, so the population for the next period, n plum, let's use a different color. N plum equal to n, the current period population, times 1 plus n, the lowercase n. So basically, the lowercase n is a population growth rate. Okay, so suppose n equal 3%. That means the population will grow in a rate of 3% each period. Okay, here we define it as period. Period can be year, can be decade. It doesn't matter how you define it, just a period. Okay, and we only doesn't allow n to be lower than or equal to -1, because if it is -1, obviously the population next period would be 0. That is not allowed. We allow, for example, the n equal maybe -3%. That means our population is growing down, not growing up. Okay, which is the case right now in Taiwan. Okay, so in the Solow growth model, population is assumed to grow at a constant rate. Point here is constant. Okay, and the consumption saving behavior. Now we have a consumption saving behavior. Okay, before there's no saving. Remember, here we have a saving behavior. So basically, there will be a output y. And this y output is the total output. And the consumption will be just 1 minus s times this y. That means the s times y part is the total saving. Okay, so we have c plus s equals y. The capital C and capital S means the total consumption and the saving. That adds up to the production y. And the relationship is assumed to be a constant fraction of the y that is going to be the saving, and also a constant fraction to be the consumption. Okay. So again, this is very simple assumption, but these assumptions allow us to focus on something that's more complicated. And also, this is also kind of like the question that you guys were asked in the midterm exam. You should notice that the lowercase n and lowercase s here, the saving rate and the population growth rate, they are exogenous variable. They're not endogenous. Endogenous means it will be determined by the input and the exogenous variable. Okay, they're like if you solve a xy equation, the xy there are endogenous. But here, these are more like the ax plus by. Those a and b, they're constants that are predetermined. Okay, so we'll say in this kind of model, the population growth is what? Is exogenous. And the saving behavior is also exogenous. Okay, and recall from Martian's model, we determine how the population is growing over time, right? So in there, the population grows. Although in the steady state, there's no population growth, right? But that's endogenous. That's determined by the model. Before, the Martian model doesn't assume that population will not grow in the steady state. It is a model solution, sort of, the equilibrium concept in that model, right? Now, there's a big difference between these two. Okay, and how does that Y produce? Okay, actually, Y is produced by a production function from the firm, and you should, look at this production function and feel very familiar, right? It is again a constant return to scale production function, and use the input capital and labor. Okay, it's just that the labor here we're not talking about a unemployment model, so we assume that everybody's gonna work, sort of. So total population is going to go into that production function, and there's capital, which is and how does that? Sorry, forgot to say that first. So constant return to scale gives us what? We can divide everything by the number of population, the capital N. And so Y divided by N is this. It's the lowercase y. We sort of always use the lowercase as the per capita number, and the uppercase as the total number, total sum. Okay, so yn, and that's what this is divided by n. This whole thing is divided by n, and since this is constant return to scale, this n can go inside, so it becomes k divided by n and 1. And k divided by n is just lowercase k, right? And we can rewrite the f of lowercase k1 as f of k. This technique we've used before, right? Because we convert a function with 2 variables into a 1 variable function, we rename that function so that it looks like just a 1 variable function. It makes the equation simpler. Okay, so lowercase y equals z times f of k. And what about the capital? How does this capital be determined? The n, we already know that the n population is growth over time with a constant rate of growth, right? But how about capital? So here, capital is decided by the next period capital is decided by the last period capital times 1 minus d and plus an I. What does that mean? The lowercase d is called the depreciation rate. Okay, it's like your car or your computer. It will have some depreciation over time. Usually, like the car, they usually say that when you buy a new car, when the car hit the land, you have a 20% depreciation. 20% of the value is gone. Okay, or think of like more real capital, like your factory, the factory machine, that kind of thing goes old. Okay, so it doesn't pretend a constant value over time, so it depreciates. It got less worth of money, basically. So in this period, we sort of inherit from last period some amount of capital. And this amount of capital will depreciate first. So 1 minus d of the previous period capital is transferred to this period. And then in this period, we will add some more capital. And the add amount is called investment. Is I. Okay. And by the way, this is a common misunderstanding, but you guys should have learned this in a previous class somewhere. This is what economists usually means by investment, real investment. That's the accumulation of capital. And the usual term investment, when most of the other people who didn't study economics talking about it, they mean something like stock market, okay, or even foreign exchange market. You invest in U.S. dollar and hope for return in the future. But in economics, when we talk about investment, we talk about this kind of real investment. Okay, so this is the capital K here is a flow variable. Every period, I will have some amount of capital. And that amount of capital will transfer to the next period after depreciation. And in each period, I will add some more capital to it. And this added amount is called investment. Okay, so we keep adding. Otherwise, if the capital just keep depreciate, it will eventually become zero, right? So it won't add up. We won't have any accumulation. Okay, and this is the function for the lowercase y equals z times f of k. Notice that this is a one variable function, right? So you can draw this on this simple 2D graph, where the x-axis here is the capital per worker, and the y-axis here is the output per worker. Okay, and you will notice that the slope, that is basically z times f plum of k, will equal to MPK. And what is MPK? Remember, MPK is basically z times partial k partial f of kn. Okay, so by the graph, you should, you sort of have the idea why it should be the case, but why is it really the case? So if you want to prove that z f plum k equals MPK, we start with what is the definition of MPK, as I just noticed. MPK is z times partial k partial f of kn. Okay, and since this f function is constant return to scale, I can take the capital N out. That's this step. I take the N out, and here it becomes kn1. And then I define this as f of lowercase k, right? So this step, I just replace this with this. Okay, and this is chain rule. So partial k, this one, partial k partial f of k equals f plum of k, and partial lowercase k partial capital case k and lowercase k. This thing. This is capital case k, uppercase k. This is lowercase k. Okay, but lowercase k is just this by definition, right? So if you partial k partial this is basically partial k partial kn, and that's just n over 1, right? So this thing is n over 1. 1 over n, sorry. 1 over n. And so the whole thing should be f plum k divided by n. But if we replace if we replace this with this, if this is f plum of k divided by n, then this n and n will cross out. So this whole thing will become z times f plum of k, right? Any questions? I mean, it's first year undergrad calculus. And it's not really the difficult one, right? It's not like those partial derivative we did before. But, I mean, you should know what you're doing. I mean, some students, they read the textbook and see, okay, so, or this one, you just see the slope equals MPK, okay, I just memorize it. It doesn't really help. If you want to learn something so that it can help you in the future, then you should understand all the logic behind it. That's what you will really learn something. Okay? Okay, so if there's no further questions, in this model, the income expenditure identity is quite simple. Okay, so the capital, the output is spent on two things. One is consumption, one is investment. Okay, you might ask me, didn't you say y equals to c plus s? Why now it become c plus I? The key here is that S equals I. Saving equals investment. And the reason why I write I here is because this is an income expenditure identity. This is how money is spent. Saving is not a spending. Okay, so where does those investment come from? It is not just coming from, nowhere, or coming from God or something. Those investments are from the consumer's saving. Those savings become investment. So saving become investment. That's the key. So since saving equals investment, I can write k plum equals sy plus 1 minus d times k. This used to be what? This used to be investment, but investment is just saving, right? And saving is just s times y. Okay? And if we have this, and if we substitute the y with the z times the production function, and then we can rewrite this in a per worker form, because we want everything to be per worker form. We divide everything with n. If we divide, but this is a tricky part here, okay? If we divide n here, and n here, this part is fine. This becomes 1 minus d times the lowercase k. And this one becomes this szf of k. That's perfectly fine. We did it already before. But what about here? Why it didn't just become this? That's because this is defined as k plum divided by n plum. That's the next period population. But what we have here is k plum divided by current period population. So we need to do a bit trick. We basically put a n plum here and n plum here, so that it can actually cancel out. Okay? And by doing that, I know this is lowercase k plum. And this is 1 plus n, as we define in the first equation in this model. That's the population growth rate. Remember, n plum equals 1 plus n. So if you divide over here, then that's 1 plus lowercase n. And then I can move this 1 plus n to here. You will get an equation looks like this. That's the next per worker capital equals what? SZF of k divided by 1 plus n and 1 minus dk divided by 1 plus n. Why is this equation important? Because it tells you what? It tells you in the equilibrium the relationship between k and the k plum. Right? Because if you have the k here, you insert the per worker k inside this function, you will notice that other variables here are all exogenous variable. Right? The lowercase d, n, z, s, the f function, those are all exogenous. The only thing you didn't know yet was the per worker k. But now if you have the per worker k, and if you insert into it, you will have the next period per worker k. And if you have the next period per worker k, you can get that number and insert back into this function. And you will get the sort of k double plum. That's the per worker k in the next 2 period. Right? So basically, you can have a relationship, a function that tells you the relationship between the k and the k plum. And we have used this technique before. To find the steady state, you will draw a 45-degree line and see where this function crosses the 45-degree line. Because what that means is this k star, if you inside the k star into input the k star into this function, the output will be exactly k star. Right? So basically, this is the definition of steady state. Right? If this society has a per worker capital level that's exactly k star, then next period it will be k star again. And next period it will still be k star. And from that point on, it will always be k star, unless something else change. Okay? Okay. Any questions so far? Okay. And since we have this, that's in the steady states, the k star equals SZF of k star, and the whole bunch of all that, these things. We can separate this into 2 parts. One is the n plus dk, and the other is this SZF of k. And these two functions will intersect at this point. We call it K1 star. Understand what I'm doing? I see some confused face, so I'm not sure. Okay, 2 minutes to the break, so let's have a break now. We'll talk about this when we come back.